Hello everyone, I am Eshan Tripathi, Physics Faculty at askIITians, and now we are going to continue with the second lecture of the chapter Work, Energy and Power of grade 9. So we in the previous lecture have already started, we have already learned the work's definition, what work is, and what positive, negative and zero work also is. Basically the work done by a constant force, how to find it, we learned that. So in this lecture, we are going to continue further and we will study first of all what kinetic energy is, and then later on we're going to move to what work energy theorem says. So we're going to see that. So the first topic, as I mentioned, is kinetic energy only. So kinetic energy of a body of an object is the energy possessed due to its motion. So you guys must have a bit of idea of kinetic energy. You must have heard it somewhere. If body is moving, we say that it has some energy because of the movement of the object. We say that it has some associated energy with it. So that energy is called kinetic energy of the body because the object is moving. So kinetic energy, as is written over here, is half mv square. Basically, kinetic energy is half mv square, where m is the mass of the object and then v is the speed of the object. So kinetic energy is defined as half times the mass of the body multiplied by its velocity square. So what do you guess should be the SI units of this? Looking at this formula, half mv square. So if you would see that kinetic energy is half mv square. Let me write it over here. Kinetic energy is half mv square. So what is the SI unit of mass? Mass is SI unit we know is kgs. And what is the SI unit of velocity? That is meters per second square. So can I say SI unit of kinetic energy is masses SI unit, which is kgs, and velocities of not velocity, sorry, speeds SI units, which is meters per second. It's square, meter per second square. That makes it kg meter square per second square. Isn't it the same SI unit that we had for work? Work also had the same SI units, kg meter square per second square. That means since we used to call kg meter square per second square as joules, we can say SI unit of kinetic energy is also joules. In short, represented by the symbol J. So this is interesting. Kinetic energy has the same SI unit as work. Actually, there's more to it. We are going to study that later on also. But my question over here could be, what do you guess? Kinetic energy should be a scalar quantity or should it be a vector quantity? Think about it. Is it going to be scalar or is it going to be vector? See, mass is a scalar quantity. Speed is a scalar quantity, and that has been squared. So scalar multiplied by square squared. So it's going to be scalar quantity only then. So kinetic energy is also scalar quantity. An example of it, look at over here. Like if you have mass of there's an airplane which is flying, which is having a mass of 40,000 kgs and speed of 242 meters per second. You can calculate that's kinetic energy also, right? So just put kinetic energy as half times mass, which is 40,000 multiplied by 242 square. This much joules of kinetic energy this airplane possesses with this much mass and this much speed. In which direction? In which direction is it having this kinetic energy? It does not make any sense because kinetic energy is a scalar quantity. It does not have any direction. So this is what kinetic energy is. Very mathematical as of now. It's just an energy because an object is moving. Why we are defining it like this, we will see that later. So let us move to let's move to a question on this. Let's look at this. If the speed and mass of an object are doubled, then which of the following is true? The momentum of object is doubled, kinetic energy of object is doubled, momentum is quadrupled, kinetic energy is multiplied by 8 times, or momentum and kinetic energy both are quadrupled. What do you guess? We are saying from mass m, it becomes mass 2m. And from speed v, it becomes 2v. Speed also gets doubled, mass also gets doubled. So let us look at it. Momentum we know is mv. So what will be the new momentum? New momentum is going to be new mass multiplied by new speed. That is going to be 4 mv. So it seems like momentum of the object is quadrupled. That's correct. And then after that, let's talk about kinetic energy also. Kinetic energy, as we know, is half mv square, which we just learned. Just a second. Yeah. Kinetic energy is half mv square. Originally, it was also half mv square. But what is going to be the new kinetic energy? Ke dash. Pretty simple it is. The new mass is going to be 2m. So half into 2m into new speed, which is 2v's whole square. That comes out to be 4mv square. So how many times of the original kinetic energy is this quantity? Like original kinetic energy was half mv square. New kinetic energy is 4mv square. So from this, can I deduce that the new kinetic energy Ke dash is 8 times of older kinetic energy? Yeah, so that means option D is also the correct option. So both these two. Okay, I think that's pretty simple. Just one formula we used, nothing great about it. Okay, then let's look at this question. There is a soccer ball with mass 2.1 kgs. The ball leaves the ground moving with speed 30 meters per second. What is the kinetic energy of soccer ball? Again, a very simple question. The soccer ball thrown up with speed 30 meters per second, having a mass of 2.1 kgs. Now, actually, the direction doesn't even matter if you realize it. All that matters is the speed. Whatever direction it is thrown in does not have any significance. Basically, kinetic energy is half mv square. In this case, it is half into mass, which is 2.1, multiplied by speed square. So 30 square is 900. So this is going to give us, how much is it going to be? 900, is it? Divided by 2 joules. No, something wrong. Just a second. No, it's fine. It's fine. Yeah. It's 945 joules. That is how much it's going to be. So yeah, it's simple. Nothing great about this. Okay. Now let's move to the next thing. We'll move to some good questions also on this. Don't worry about it. First of all, we have just defined what kinetic energy is. And now let's see why we are even learning kinetic energy. There is a theorem called work energy theorem. Let us see what it says. It says that work done by all forces on an object is equal to the change in its kinetic energy. Let me give an example for this. Let's say there's an object. Object has mass of 2 kgs. Okay, then I give it a push. I give it a push, that is, I give it a force of 10 newtons. Now, if 10 newtons is the force acting on a 2 kg block, and let's just assume that the surface is smooth, how much is going to be the acceleration of the block? Acceleration is simple to find. Net force divided by mass, that is 10 divided by 2, that is equal to 5 meters per second square. This body will start accelerating with 5 meters per second square. Let me say originally the body was at rest. So if this body, which is originally at rest and starts accelerating with 5 meters per second square, could you tell me that by the time it displaces by, just a second, yeah. The question is, by the time it displaces by, let's say, 10 meters or 10, let's make it 40 meters. By the time it gets displaced by 40 meters, What do you think from equations of motion should its velocity be after a displacement of 40 meters? Think about this. Object is at rest. Acceleration is 5 meters per second square. Basically, initial velocity is 0, acceleration is 5, and displacement of the body is 40. We have been asked the final velocity. Which equation of motion would we be willing to use? We are going to use the third equation of motion. V square minus u square is equal to 2as. That gives us v square minus 0 square is 2 times displacement, which is 40, times acceleration, which is 5. That gives us 400. So this gives us the value of velocity after displacement of 40 meters is 20 meters per second. So after this much displacement, the body is moving with a speed of 20 meters per second. Now let's see something interesting. How much is the work done by the force? What is the work done by the force? The work done by the force comes out to be 10 newtons of force was acting over 40 meters displacement. So can I say that the work done was positive 400 joules? 10 multiplied by 40 cos of 0 degree. Now let's talk about the initial kinetic energy. Initially, what was the kinetic energy of the body? I'm going to write it as KEI, initial kinetic energy, and that's half m into initial kinetic energy means initial speed square, half m u square, and u was 0. So initially there was 0 joules of energy, kinetic energy. And after whole of this motion, what is the final kinetic energy? Half m final speed square, half m v square. That is half into mass is 2 into speed is 20. It's square. That comes out to be positive 400 joules. Notice anything interesting? How much is the change in kinetic energy? How much is the change in kinetic energy? Final kinetic energy minus initial kinetic energy. Change is anything which is like change is always final thing minus initial thing. So the change in kinetic energy is 400 joules, which is actually equal to the work done by the force. That is what this theorem is trying to say. Work done by all the forces on the object. Now, let's say we consider only one force. What about other forces? Other forces, normal reaction, which is upward perpendicular, gravity, which is mg again perpendicular, they do not do any work. They are at an angle of 90 degree. Their works were already zero. So net work done by all the forces on this body is actually equal to the change in its kinetic energy. That is what this theorem says. Understood? So if somebody is doing work, somebody is putting in efforts, technically what they're saying is that effort is being delivered in gaining its kinetic energy. The whole job of doing the work is that its kinetic energy should increase. That's what, and that is why the units were also same. Work done was also in joules, kinetic energy is also in joules. But you would say maybe that's coming out to be in this case. We want a mathematical proof of this. Proof is also very interesting, guys. Let's see, let's look at the proof. Um, Actually, this work energy theorem is being derived from one of the equations that we know. In fact, the equation that you used to solve the previous question, the third equation of motion. Work energy theorem can be derived from third equation of motion, which is v square minus u square equals to 2as. I actually like to write it while deriving this 2as on the left and v square minus u square on the right. Now let's see what we can do. We'll divide both the sides by 2. What will we get? As is equal to v square minus u square by 2. Then I'm going to multiply both sides with mass also m. Let us do that. So MAS is equal to, can I say that becomes half mv square minus half mu square. I have multiplied both sides with m and then I split this numerator into two parts, v square minus u square divided by 2 each. Now what is m into a? This thing over here. What is this m into a? Isn't it The net force acting on an object is mass into acceleration. That into displacement is equal to, net force into displacement is equal to half mv square minus half mu square. And think about it. What is net force on the body multiplied by its displacement? Isn't that net work done on the body, which is final kinetic energy half mv square minus initial kinetic energy half mu square. And that is what the work energy theorem is. Net work done by all the forces is the change in the kinetic energy of the body. Delta represents change. This is work energy theorem. So technically, if you would see, work energy theorem is nothing new. It is another way of writing the third equation of motion. It's another interpretation of it. But it's interesting. So I hope this is clear. After this, maybe we can look into some more questions on it. So let's see this question. There is an 8 kg block which is moving with speed of 3.2 meters per second. So let's draw this. There is this horizontal surface. There is an 8 kg block kept on it. It's a bit darker. I think I chose the wrong pen. And it is moving with a speed of 3.2 meters per second. Now, a net force of 10 Newton is constantly applied on the block in the direction of movement. So this body was already moving with this speed. If no other force was acting, it would have continued with the same speed. Why? Law of inertia. A body, unless an external force is applied on it, will continue to move in same speed. Now we are saying that a 10 Newton force is applied on it externally. Okay, until the time it has displaced by 16 meters towards right. Until the time it displaced by 16 meters, constantly we kept on applying this 10 newtons of force. So what would happen in that time? The body would accelerate now. A force is acting. So this body is going to accelerate. But that's what we are going to find the final velocity. But this time we do not have to use the acceleration approach, since we have just learned the work energy theorem. We are going to use it to solve this. So let's see. According to the work energy theorem, the work done on the object can. According to work energy theorem, the work done on the object goes into the change in its kinetic energy. That is final kinetic energy minus initial kinetic energy. What is the work done on the object in this case? That is force 10 newtons multiplied by displacement 16. 10 into 16 cos of 0 degree. That's 160. That is final kinetic energy minus initial kinetic energy. That's half into mass into final velocity square, which we are supposed to find, minus half into mass into initial velocity square, which is 3.2 square. So on the left side, we have 160. Here we have 4v square. And then here we have, how much is it? 3.2 into 3.2, 2 to 4, 3 to 6, 3 to 6, 3, 3, 9, 4, 2, 10. Okay. I'm very poor at these calculations. Multiplied by 4 also, 4, 4, 16, 8, 9. I think 40.96. So basically, V square will come out to be 160 minus 40.96 divided by 4. So solving this, you'll get the value of V. You would notice that if you use the third equation of motion also, you would get the very same answer. Okay. So you can try this by yourself. You use the equations of motion and get the same answer. You will get the very same. Okay. So after this, let us move to the next question. A 5 kg block is given a velocity of 10 meters per second along rough horizontal surface. Now this time the surface is not smooth, it's rough. 5 kg block, coefficient of friction is 0.5. So the question is, how much is the distance traveled before it stops? It was originally given the 10 meters per second. So guys, you can imagine the only force acting which is going to oppose it or like cause or oppose the motion is the friction force in the backward direction. Friction is going to oppose its motion and eventually the block might come to rest. With friction? Kinetic friction because body is already slipping. So eventually after some time, body is going to come to rest. We have been asked the distance L after which the body stops. So again, we are going to use work energy theorem only. We will say that the work done on the body is equal to change in its kinetic energy. That is final kinetic energy minus initial kinetic energy. Okay. Now question is how much is the work done on the body? The force acting in this case is friction, which is backwards, and displacement is L towards right. So can I say that the work done is the magnitude of kinetic friction, magnitude of the displacement multiplied by cos of angle between them, which is 180 degree. That is equal to final kinetic energy half mv square minus initial kinetic energy half mu square. And since we know body is at rest finally, can I say final velocity v is zero? This quantity is zero. This means Fk into L is equal to half mu square because cos 180 degree is also minus 1, minus on the right, minus on the left get cancelled. And you know the value of kinetic friction also. That is coefficient of kinetic friction multiplied by normal reaction. Now see guys, here only one kinetic coefficient of friction is given 0.5. So which one is it? Static or kinetic? Whenever it's not mentioned which coefficient of friction is it, it is assumed that both are equal because as you know, coefficient of kinetic friction is less than equal to coefficient of static. They can be equal. So whenever only one of them, when only one is given and it has not specified which one it is, it's obvious that both of them are equal and equal to 0.5, the given value. So in this case, normal reaction is again mg, only a downward force acting is mg, that will be balanced by normal reaction. So it's 0.5 multiplied by m, which is 5 multiplied by g, which we are assuming 10. So that is 25 newtons. Okay, so kinetic friction is 25 newtons. L we do not know. We have to find it. Half into mass is given to be 5 and distance, initial velocity is going to be 10. So 10 square. So it turns out that L is equal to 10 meters. After traveling a distance of 10 meters, the body is going to stop. So that's how we can do this in case of negative works also. And now let's look at this last question on this, last numerical. A small block of mass m is projected on a smooth inclined plane with velocity v naught. Let us assume angle is theta, that needs to be given. Mass m is there and it is given a velocity v naught. It is projected up on a smooth inclined plane with this velocity. This is smooth. So you can imagine as it moves up, gravity is going to pull it down. So with time, it's going to get slower and slower. And finally, at the top, if you can imagine, it will come to rest. We have been asked this time, what is the distance L over the inclined plane? Like along this inclined plane, what is the value of the L after which it stops? Think about this. How can we do this? Okay, let's see. If we look at the free body diagram, we need to consider all the forces because see, again, in the end, we are going to use work energy theorem only. We are going to say that work done, net work done on the body because of all the forces which are acting is final kinetic energy minus initial kinetic energy. That is half mv square minus half mu square. Now let's see. We are over here. The main problem is finding out the work done, net work done on this body when it has displaced by distance L over the inclined plane. See, we know mg force is acting downwards. Mg force is acting downwards. Any other force acting on it? Yeah, one more force is acting, which is normal reaction, perpendicular to inclined plane like this. As we have done in previous chapter also, laws of motion also, we can actually break this mg into two components now. We can break this mg into two components. One component would be, since we know that this angle will be theta, using a bit of geometry, you can find out the angle that this mg vertical forms with perpendicular to inclined plane. That will be theta. So mg cos theta is going to be the component. Okay, I'll draw this again. A second. I'm going to break this mg into these two components. So normal reaction is still acting like this, but when mg's components are taken, one component will be mg cos theta in this direction, another component would be mg sin theta in this direction using trigonometry. So look at this, mg cos theta like this, mg sin theta like this, normal reaction like this. And the body is getting displaced in the upward direction by distance L. So now I have broken this into three forces. One is normal reaction, another is mg cos theta, one is normal reaction, other is mg cos theta, other is mg sin theta. Now, which of them will be doing work over this displacement L? Look at this. Since normal reaction is at 90-degree angle to this displacement L, it is perpendicular to it. So it won't be doing any work now, as we discussed in the previous lecture. And mg cos theta is also perpendicular to it. Mg cos theta will also not do any work. The only force that will do work is this mg sin theta. And that too, it is in opposite direction. It would be doing negative work. So the net work done on the body is going to be simply mg sin theta, the force in the backward direction, multiplied by distance displacement L in the upward direction, and cos of angle between them. That angle is 180 degree. That means on the left, minus mg L sin theta is equal to half mv square. Guys, finally the body comes to rest at the top. So v is going to be 0, isn't it? So it's going to be 0 minus half m. What is the initial velocity of the body? That is given v naught. That means mg L sin theta is equal to half mv square, v naught square, m cancels m, and we get that L is equal to v naught square by 2g sin theta. And that's the final answer that we get. So the body is going to stop after moving on the inclined plane through a distance of v naught square by 2g sin theta. I hope that is clear to you. So with this, that's it. That is the second lecture of work energy, work, power, and energy. We learned work energy theorem, and in the next class we're going to learn another form of this work energy theorem, but we'll discuss that later. And if you have any doubts, you could post the question on the batch discussion forum PDF, and there this could get answered. Thank you so much. Have a great day.